In this video, we'll discuss the adiabatic approximation, another time-dependent approximation. We'll start with defining adiabatic processes. We'll talk then about pendulums, in particular the Foucault pendulum. And finally, we'll prove the adiabatic theorem. So what are adiabatic processes? Well, a good definition is that when external conditions change gradually. So a process where external conditions change gradually, or a process where the characteristic internal time constant is much shorter than any external time constant. So these two are basically the same, assuming that your internal time constants are rapid compared to the outside change. And the next question is, how do we analyze adiabatic processes? Well, in classical physics, we treat the external parameters as constant and allow them to vary slowly with time at the end of the calculation. In quantum mechanics systems, you use the so-called adiabatic approximation, which is what we'll prove later on. One example of this we already have discussed, which was the hydrogen molecule ion. And we held the nuclei at rest, realizing that the nuclear motion is much slower than the electron motion. Then we calculate the electronic state, and then we use the electronic state to compute the equilibrium position of the nuclei, and then you could iterate this to get the entire motion. This is the so-called Born-Oppenheimer approximation. So, a pendulum is an excellent example of adiabatic processes. Let's consider a pendulum at the North Pole, which is swinging along the longitudinal direction of Portland, Oregon. So you can see the pendulum is swinging in this direction. Portland's down here. You carry the pendulum down past Portland, all the way to the equator, along the same meridian. And then you go east along the equator to a second meridian over here and back to the North Pole. When you do that, you'll see that the pendulum is now swinging at an angle theta, where this is the angle subtended by your trip along the equator, east of the Portland meridian. The angle theta is related to the solid angle subtended by the path of the pendulum, which is omega, which is the solid angle subtended by this green path here. We can see this relationship by computing the area enclosed by the pendulum path. Well, we start with the area of a sphere of radius r. So the area of a sphere of radius r is 4 pi r squared. We divide it by 2 since we're only talking about the northern hemisphere. Then we take the fraction that theta is of the entire 2 pi rotation, so that's theta divided by 2 pi. And that's equal then to, if you calculate all this, it's going to be the pi's cancel, the 4 cancels the 2 and leaves a 2, so you have another 2 here, so those cancel, and you have theta times r squared. Now, if we scale it to the unit sphere to get the solid angle, that means that r goes to 1, then you have theta is equal to omega, which is a solid angle. More generally, omega is just the area subtended by the path divided by r squared. So for an arbitrary path, you can calculate this by just doing an integration along the path. And if you integrate this around the path, then divide by r squared, you've got your solid angle. So the solid angle there is omega is equal to the path integral, the closed path integral of d omega. But this is simply sine theta d theta d phi, and therefore we can calculate the solid angle. So a specific instance of this kind of situation is a Foucault pendulum. So let's imagine a Foucault pendulum sitting at a particular latitude, which is where the blue line is. With the Foucault pendulum, the rotation of the Earth itself carries the pendulum along a closed path. So if you start here at the beginning of the day, you go around all the way, it comes back to the same location in a fixed reference frame after one day. So each day you go along a closed path, which is shown in blue. Well, we want to integrate the angle subtended by that path, which is equal to that closed loop integral over sine theta d phi. Well, that's easy enough. You go from 0 to 2 pi because you go an entire rotation along the phi axis. So that goes from 0 to 2 pi. But the angle that we're interested in is sine theta d theta, whereas the integration goes from 0 to theta, 0. And so when we do that integration, we get 2 pi from the first integral over d phi, and then you get minus cosine theta evaluated from 0 to theta 0. That gives you 2 pi times 1, which is what you have when theta is equal to 0, minus cosine of theta 0. At the equator, theta 0 is simply pi over 2, so you get 2 pi, because this is 0. And at the pole, you get omega is equal to 0, because at the pole, your rotation is basically around your own axis. In Chicago, where we are, where our latitude is 48.16 degrees, cosine of 48.16 is 0.667, and so omega for Chicago is about 2/3 pi. So this kind of pendulum, and any kind of these processes, are so-called non-holonomic processes or non-holonomic systems. They do not return to their original state when carried through a closed loop. So what happens with the Foucault pendulum? As it goes through a full loop, the pendulum rotates with respect to the axis that it's sitting on in the museum, for example, at the Museum of Science and Industry, or whenever you set up a Foucault pendulum in a big stairwell. As you rotate around, that Foucault pendulum rotates, and after one full day, it's back to where it was before. So these are non-holonomic systems. So we want to look at this adiabatic theorem and show that, in fact, it works for quantum mechanics. So let's start by considering a time-independent Hamiltonian and its nth eigenstate. So the eigenvalue equation is h applied to psi n is equal to e sub n psi sub n. With time, this state evolves, picking up a phase factor, because there's a time dependence in the time-dependent solution, which depends on the energy, because we've separated these, the energy and space, the time and space, and so our separation constant is the energy, and we've assumed a solution e to the minus I e sub n t over h bar. And so we have this, that the time-dependent wave function is equal to the stationary state times e to the minus I e sub n t over h bar. And so as time goes on, there's a phase factor that gets picked up, which is e sub n t over h bar. Now, let's imagine that instead the Hamiltonian itself varies with time. So stationary state eigenfunctions and eigenvalues also have to vary with time, right? So if h varies with time, then psi has to vary with time, and e has to vary with time. Everything has to vary with time. So now my eigenvalue equation says h of t applied to psi sub n of t is equal to e sub n of t times psi sub n of t. But we're going to say that all the way through this variation, the eigenstates, the different eigenstates remain orthonormal and complete, even while they're changing with time. And this time dependence is going to be slow. So we can write, because these are going to remain orthonormal, we can write the psi n of t inner product with psi m of t is equal to delta sub nm. Therefore, the solution to the time-dependent Schrodinger equation is where we have to put in the full time-dependent solution. And now we have two time dependences. We have the time dependence that depends on the energy, which depends on time, and the time dependence in the solution itself. So we have IH bar partial with respect to t, psi of t, capital psi of t, is equal to h of t, psi, capital psi of t. And we're going to write this equation, the solution to this equation, as a sum, as an arbitrary state is going to be a sum of eigenstates with coefficients. So we have sum over n, c sub n of t. Now this has to vary with time also because everything's varying with time. Psi sub n of t, e to the I, theta sub n of t. This is my time-dependent phase factor, which is related to the energy of the nth state. But remember, the energy of the nth state varies with time. And so theta sub n of t now turns into an integral, because at every time the energy might change a little bit, and so the time dependence is going to fluctuate. So theta sub n is minus 1 over h bar, integral from 0 to the time of interest, t, e sub n of t prime, d of t prime. And this takes into account the change of energy as a function of time. And that gives you a built-up integration phase factor that depends on time, t, but it's sort of the sum of all the energies that come up to that time, t. Theta sub n of t is called the dynamic phase factor. And as you can see, the dynamic phase factor depends on energy alone. So we have our solution to the time-dependent Schrodinger equation, with all time dependence everywhere, and we have our time-dependent phase factor, which is the integral of the energy up to the time of interest. We can now apply this solution to the time-dependent eigenvalue equation. Remember, the time-dependent eigenvalue equation is IH bar, partial with respect to t, psi of t, is equal to h of t, psi of t. Well, we now have to take the time derivative of the left side. And so each of these has time dependence. So we're going to have three different terms. The first term is Cn dot of t. Then the second, and psi sub n, and then we have e to the I theta sub n of t. I've dropped the t's just to make it a little shorter. Then we have c sub n, psi sub n dot, so the time derivative of psi sub n, times e to the I theta sub n. And then we have to take the derivative here, and we'll get I times c sub n times psi sub n times theta sub n dot, because we have to take the derivative of the exponential. That brings down a theta n. We have to take the derivative of that and an I. All, again, times e to the I theta sub n. And that, on the right side, is equal to h of t applied to psi of t. And psi of t being this, we can apply h on the outside, pull this in. H does not act on the coefficients. It acts on the eigenfunctions. And so you get sum over n, c sub n, h applied to psi sub n, e to the I theta sub n. Now, if we look at the definition of theta sub n, if we take the time derivative of theta sub n, we just get the energy, E sub n of t. And so times 1 over h bar. So we can replace theta dot, sub n dot, with minus 1 over h bar E sub n. And that's what we do here in blue. So we get this term is the same, this term is the same, this term gives me now minus I over h bar C sub n, E sub n, psi sub n. Remember, they all have time dependence. On the right side, when we apply the Hamiltonian to psi sub n, we just get the energy, E sub n, because this is part of the eigenvalue equation, right? These are eigenvalues of the Hamiltonian. Now, of course, E sub n varies with time as well as psi sub n. Clearly, we can erase, because these are all within the sum, this term is exactly equal to this term. They can be canceled. We're then left with two terms, this term here and this term here. So we can then bring one over to the other side, and we get the sum over n, c sub n dot psi sub n e to the I theta sub n is equal to minus sum over n, c sub n psi sub n dot e to the I theta sub n. This is the equation we have to solve. Now, if we take this inner product with a different eigenstate, psi sub m of t, that's implied, we get the following. Because of orthonormality, and we're forcing orthonormality on these time-varying functions, you get on the left side the sum over n, c sub n dot delta sub mn e to the I theta sub n is equal to minus sum over n, c sub n times the inner product of psi sub m and psi sub n dot, so the time derivative of psi sub n, times e to the I theta sub n. So we can see that the left side term, because of the delta function, reduces to one coefficient, that is c sub m, and one phase factor, e to the I theta sub m. And so we get c sub m dot e to the I theta sub m is equal to minus sum over n, c sub n times the inner product of psi sub n with psi sub n dot e to the I theta sub n. So this is our definition. Now, we can bring the phase factor from the left side over to the right side and pull it into the to the sum. So we get, as a last term, everything else is the same except e to the I theta sub n minus theta sub m. And this is just one. This is varying according to the sum. Now, this bracket on the right needs to be calculated. And we can start by looking at the eigenvalue equation for the nth state, psi sub n. Well, h of t applied to psi sub n of t is equal to e sub n of t, psi sub n of t. If we take the derivative, the time derivative of all these terms, we have h dot psi sub n plus h times psi sub n dot equals e sub n dot psi sub n, and then plus e sub n psi sub n dot. What we're interested in is finding out what psi sub n dot is. If we now apply an inner product again with psi sub m, where m is not equal to n, then we get the following out of these four terms. We get inner product of psi sub m, h dot, psi sub n, plus inner product of psi sub m, h, psi sub n dot, equals e sub n dot, inner product of psi sub n, psi sub n, plus e sub n times the inner product of psi sub m, psi sub n dot. Well, clearly what we can do is we can bring this term here over to the left side, because the Hamiltonian is Hermitian. So when you apply it over to the left side, you'll get psi sub h applied to psi sub n. Then we know that this, because these two are orthogonal, since m is not equal to n, this term cancels. We can then get e sub m, which we pull out from this term. And now we can bring both the e sub m term and the e sub n term, which have the same inner product together, to the same side. And so we get e sub n minus e sub m quantity times the inner product of psi sub m, psi sub n dot, is equal to the final term that's left on this side, which is psi sub m, h dot, psi sub n, all inner product. So the bracket in the sum for n not equals to m, this term here, is now exactly this term here. And so we can write that as psi sub inner product of psi sub m times psi sub n dot is equal to the expectation value or matrix element of h dot, so the time derivative of h, with the mth state and the nth state, divided by E sub n minus E sub m. So we now have a defining equation for C sub m dot, which depends on C sub n, the sum over C sub m, n rather, the inner product of psi sub n m with the time derivative of psi sub n, e to the I theta sub n minus theta sub m. And we know for n not equal to m what this inner product is. It's given by psi sub m h dot psi sub n over E sub n minus E sub m. Now, for m is equal to n, the phase factor is exactly 0. And therefore, the bracket can be taken out of the sum and evaluated explicitly. So, we know what this value is for n not equal to m, but for n equal to m, then this gives you 1 because theta n and theta m are the same in that case. This has to be evaluated. But now because it's theta sub m, psi sub m, you could take it out of the expectation, out of the sum. Well, we know that C sub m dot is equal to, when m is equal to n, this reduces to one term only. So it's C sub m dot is equal to minus C sub m, inner product of psi sub m with its own derivative, minus all the other terms, because all the other terms have m not equal to n, and so they have a value. And here you can see this is minus sum over n not equal to m, C sub n, inner product of h dot with psi m and psi n over E sub n minus E sub m, e to the minus I over h bar, integral from 0 to t of E sub n t prime minus E sub m t prime dt prime. So this is an exact result. We haven't done any approximation so far. Now we can invoke the adiabatic approximation. The adiabatic approximation is that the time derivative of the Hamiltonian must be small. And so we're going to drop this entire second term and get a very simple answer. That C sub m dot, the time derivative of the mth coefficient, is equal to minus C sub m times the inner product of psi sub m with its own time derivative. We can now solve this by direct integration. Right, so we bring C sub m over here. We have dC sub m over C sub m is equal to minus the inner product of psi sub m with its own time derivative times dt. And this is just a number after you finish the inner product. So that means that the natural log of C sub m is equal to direct integration of this term, which is integral from 0 to t times a minus sign, psi sub m of t prime times the partial with respect to t prime of psi sub m t prime, close inner product dt prime plus a constant. Well, we know what this looks like because of the negative sign. This is going to be a complex exponential. So C sub m of t is now C sub m at the time equals 0. That's a boundary condition. Times e to the I gamma sub m t of t, where gamma sub m of t is also an integral. Is this integral here? And so it's I times the integral from 0 to time of the inner product of psi sub m t prime with its own time derivative, integrated over dt prime. So we now have a definition for the nth coefficient as a function of time. Its value at time equals 0, plus something that looks again like a phase factor. Gamma sub n of t is just another phase factor, but it's a very peculiar phase factor because it involves time derivatives and an integral. So we can now write the full time-dependent solution. We have psi of t, capital Psi of t is equal to sum over n, c sub n of t, psi sub n of t, e to the I theta sub n of t. And when we plug in everything that we know, we get that this is c sub n, the sum over n, c sub n of 0, e to the I theta sub n of t, that comes from psi sub n, the time dependence, e to the I gamma sub n of t, times psi sub n of t, which is the time-dependent eigenstate. And then we sum over n. So if the particle starts out in the mth eigenstate of h at time equals 0, with c sub m at time equals 0 equals to 1, and c sub n at time equals 0 is equal to 0 for all values of n not equal to m, then we can write the wave function psi of t is equal to e to the I theta sub m of t, e to the I gamma sub m of t, times psi sub m of t. So, what happens then? What does this show? This shows that the mth state, starting at time equals 0, with Cm is equal to 1, remains in the mth state, however that mth state has evolved, at later times t, but it picks up two phase factors. First of all, it picks up a dynamic phase factor, which just depends on the energy integral as a function of time, but it picks up a geometric phase factor, gamma sub m of t as well, which depends on this inner product, psi sub n of t prime, with its own time derivative. So this confirms the premise and shows the proof of the adiabatic approximation.